Hello everyone, my name is Zhongzhi. Today I'm going to introduce our work, Edge-Llm, enabling efficient large language model adaptation on edge devices via layerwise unified compression and adaptive layer tuning and voting. This work is published in DEC 2024 and collaborated with Zheng Wang, Yuhan Li, Haoran Ruijie Gao, Xiaoya Zhou, Shrintini Boom, Yang Zhao under supervision of Dr. Yunyan Lin. In recent days, LLMs are revolutionizing our life, such as the ChatGPT enabled by OpenAI, the powerful search tool developed by Perplexity, and also GitHub Copilot, which has been a commonly used uh, developing technique used by many programmers. And this actually stimulates a growing demand for tuning LLMs on the edge to better enable a downstream tasks that require some new domain knowledge, such as healthcare, personal assistant, and security. However, the large size of large language models actually prohibits the edge tuning, and the challenge comes from two perspectives, with computation and memory. For computation, even the state-of-the-art efficient tuning techniques requires tens of A100 GPU hours to fully tune a small-scale LLM. And also for the memory challenge, it becomes even worse that a 1.48 to 3.78 times memory gap still exists between the tuning memory needed for LLM and the edge device memory available. Specifically on the right side, we find that using two of the most commonly used parameter efficient tuning methods like LoRa and QLoRa, they always suffer from at least nearly 1.5 times memory gap. And it's also worth to know that for LoRa, like parameter efficient tuning, they have the main dominant over memory overhead comes from weights, and for QLoRa, which is a more efficient compression tuning framework, the most overhead comes from storage activation needed for tuning. So to elevate this issue, existing solutions can be categorized into three directions. The first is parameter efficient tuning, which is most commonly used as shown in the right side here, which is a LoRa module basically adapted in all of the tuning works as a baseline. And the idea is that it will add a lightweight learnable modules to in parallel with the pre-trained backweight or insert between the different layers of the LLM. And this can effectively reduce the storage for LLM when you need to scalably tune on multiple tasks and store LLM for each task. But they actually have minimal impact on memory and computation overhead. And for a second category, it's called compression and tuning, where the key idea as shown in the right side here is that they will first compress the LLM and before really tune it. So this can elevate the computation challenge because the memory, the LLM itself has been compressed, but they have marginal impact on the memory overhead. Further, compressed LLM to a lower bit width are a commonly adopted technique where they existing works always constrain the compression using same compression setting for all layers. So an open question to answer in this category is that whether it really makes sense to compress all the layers with the same compression setting. Is that possible to further reduce computation with minimal impact to accuracy? The third category is called partial tuning, where the goal is that people try to elevate the memory challenge by doing backpropagation with a reduced backpropagation depth. Specifically, they only try to update latest layers. This will achieve a limited accuracy, and also they cannot help much with the computation overhead because basically you need to tune the majority of LLM layers to achieve a better or even acceptable performance. So an open question remains is that what is there a better update methodology, specifically if we can achieve some memory efficient approach to update earlier layers in LLM? And here is a summary of existing solutions. Basically, you can find that across all the three categories, none of them can achieve um, both satisfaction to computation and memory overhead. And we summarize there are two directions to improve the efficiency. One is to compress the model, the other is to reduce the backpropagation depths, and comes with two open questions on how to compress and how to update. And in our work, we try to go further by not only answering these two questions, but also try to marry the merit of both. By answering the three questions, the third question is that how to combine the merit of them. And here it comes. Our proposed Edge-Llm framework, which achieve a benefit of computation and memory efficiency at the same time. Here is an overview of our proposed Edge-Llm framework. Basically, it's a comprehensive tuning framework for edge devices, which improves the computation and memory efficiency. And in Edge-Llm, there are three key enablers answering three aforementioned challenges. The first is on how to compress a model. We propose a layerwise unified compression technique. And on how to update all layers, we propose an adaptive layer tuning and voting scheme. The third is on how to combine the above techniques. We propose a hardware scheduling module. First, for layerwise unified compression, we are motivated by our observation that different layers have varying sensitivities to different compression techniques. Specifically, as shown in this two figure below, we realize the mean square error before and after compressing each layer in a lemma 7B model with quantization and pruning. The x-axis are the layer number and the y-axis is the MSE error. And from this figure, we basically can show that they are really diverse sensitivity to the same compression technique across different layers. So this actually motivates that a layerwise compression policy is actually needed. So our goal in layerwise unified compression is that we want to generate a layerwise compression policy based on sensitivity. And for pruning ratio, because as shown in the right figure here, the sensitivity gradually increases with the depths, and we want to keep a subtle difference between different layers, and we propose a fine-grained assignment to preserve it. And by designing the pruning ratio inversely proportional to the sensitivity. And for quantization bit widths, we propose two types of sensitivity values, and using the same bit width for most of layers and add an extra bit for highly sensitive layers. And for the second question on how to update all layers, we propose adaptive layer tuning and voting. The goal is to update earlier layers with reduced backpropagation depths. And our motivation is that existing works find Llm's intermediate layer can actually generate reasonable tokens. So we wonder that can we further extend this observation to tune intermediate layers to generate tokens. And our proposed techniques is that we'll add some skip connections between the final layer and some intermediate layers. And we'll randomly activate one of the intermediate layers that updates this layer and its preceding layers in each iteration. So although using this adaptive tuning technique itself can achieve satisfied accuracy, but we wonder that can a fine-tuned Llm even do better? Specifically, because after this adaptive tuning, many intermediate layers in Llm can generate outputs, and we try to have these intermediate layers to vote on the final output token. Because based on the motivating observation from existing work that post-softmax probability indicates the confidence, so we propose to vote for a token with maximum confidence in a max approach. Specifically, we select token with the highest probability about all layers outputs. Thirdly, after we develop aforementioned two techniques to reduce the memory and computation overhead, we wonder how can we combine both techniques and to achieve the theoretical efficiency improvement into a real device efficiency. And the challenge is that with our previously defined techniques, it will introduce some irregular computation patterns due to quantization pruning and their adaptive layer dropping. So it requires an efficient memory searching and offloading strategy. This is because it's impossible to load everything to SRAM, which only have as large as 1 megabyte of storage. So we always need to offload something to DRAM and SSD. And to this end, we propose to conceptualize LM tuning with offloading as a graph traversal problem. And our objective is that we want to identify a valid path through all blocks with minimized execution time, as shown in the red figure below. And we consider a search space, including row by row, column by column, and overlapping memory hierarchy. And we define our execution time model as the max latency among read-write latency across each memory hierarchy and computation latency. To evaluate our overall proposed Edge-Llm framework, we target a Llama 7 billion model with MMU dataset. In algorithm implementation, we consider a quantization with LMQAT and pruning with sparse-GPT. For hardware consideration, we consider a commonly used Edge-Llm setting with 1 megabytes of SRAM, 8 gigabytes LPDDR4 DRAM, and 128 gigabytes of SSD. For the evaluation methodology, we applied on top of Trita to validate hardware scheduling setup, speed up, and also we simulate with scale sim. And we observe that our proposed Edge-Llm achieves a 0.7 to 1.29 higher accuracy and a 4 times memory reduction with a comparable theoretical computational overhead compared with existing solutions. And we find that with our proposed hardware scheduling module, we achieve a 2.92 times to 3.38 times overall speed up over the vanilla implementation. For more information, please feel free to scan this QR code to our project page where we have more details, including paper and our full source code for reproduction. And thank you for your time. Here is all of our work on the Edge-Llm.